Hello, my name is Dominic Gambone, and today I'm going to be talking about the velocity of Earth's orbit and the radius of Earth's orbit. The goal of this project was to find Earth's orbital velocity and the radius of Earth's orbit. To do this, I used the Doppler effect to measure the emission and absorption lines from the star Arcturus. To begin with, I was given two shifts of the star. Shift A is shown at the top, and Shift B is shown at the bottom. Both shifts were taken 6 months apart from each other. So the methods, I used the Doppler effect, like I said before. I also created a scale factor that covered the entire plate scale. So the plate scale factor I measured it across to be 221.5 millimeters across, which I then converted into nanometers to 4.743 nanometers to help me with an equation later down the line. So this is a great picture because it shows the emission lines and the absorption lines. The first thing I did was measure distances from emission and absorption lines. All the distances in Shift A are positive, and all the distances from Shift B are negative, as they're behind the emission lines, as you can see. I only took emission lines 1, 3, 5, and 7. Yes, there are 7 of them, but I only took half. So the data, like I said, the first thing I did was measure the emission lines. So I got 1.2, 1.9, 1.5, and so forth for measuring the distance between this white line and these black lines down here. The next thing I did was I plugged those lines into the scale factor equation, which I talked about earlier, so I could convert it into nanometers. So for example, for the first one, I would plug 1.2 millimeters from Shift A into this equation. I would multiply it by the scale factor, which would be 4.743 nanometers per second, or nanometers, divided by 221.5 millimeters. Now I convert it into nanometers. And then I can pull it down to this equation, put the nanometers divided by the distance, so each emission line, shown here, had a different distance away from the sun. It would be about around 430 centimeters. So I plug that down into there and multiply it by the speed of light, which is 300,000, and that would give me the velocity of those shifts. It can be shown here. All the velocities, just like here, Shift A are positive, and all the velocities of Shift B, just like the shifts over here, were negative. And I took the averages of these two together to get these numbers over here. Now you may think to yourself, why are those numbers positive if you're just taking the average? Because wouldn't that be negative? Well, yes, if I was just adding them together and dividing by 2, but I had to use a special equation shown here. This equation is a special equation to find the velocities together. So I took 1/2 times the distance of A minus the distance of B, which a minus a negative number makes it a positive. That is why all these numbers are positive over here, and divided by 0.86 to find the average velocity of each emission line. The average velocity of each emission line is this whole line, not just the top or the bottom. So I took the average distance of 1, 3, 5, and 7, and they're all roughly, as you can see, around 30-ish kilometers per second, which gave me Earth's orbital velocity of 30.95 kilometers per second. After I found Earth's orbital velocity, I was able to use an equation using that velocity to find the radius of Earth's orbit. I plugged in 30.95 times time and divided it by 2 pi to equal the radius, and the radius is a huge number, which is extremely hard to comprehend, of around 1.5 billion kilometers. So in conclusion, the Earth is moving extremely fast. It is moving around 30 kilometers per second with a radius of around 1.5 billion kilometers. That's a lot of distance to cover. It may not seem like 30 kilometers is a lot, but it is around 67,000 miles per hour. That is my discussion on the Earth's orbital velocity and radius of Earth's orbit. Thank you.